Now we've seen some properties of random variables and of distributions, like the expected value and the variance and the entropy. And now it's time to look at very special cases of distributions, very popular and very frequently used distributions. First some discrete distributions and then some continuous distributions. And the first distribution is really a very simple one. It's the so-called Bernoulli distribution. And the Bernoulli distribution, it models, for example, a coin toss, where you have two outcomes, either heads or tails, or in a very general fashion, it models the outcome of an experiment where you can either have a success or a failure, where you would say that heads is success and tails is failure, for example. And the outcomes, it's either true or false or success or failure, and because we defined random variables to map to the real line, we have to encode this, and we usually choose the encoding of 1 and 0, like true or false. It could be -1 and 1 if you wanted to, or it could also be pi and e, but we'll soon see that 0 and 1 is quite useful. And the Bernoulli distribution, it has two values, so it's countable, and that's why it's discrete. And the corresponding probability mass function is very simple. It's mu, the probability mu, which is a parameter between 0 and 1. If it's a success, and the counter event obviously has the counter probability, so it's 1 minus mu if you have a failure, which corresponds to x equal to 0. And usually for these very popular distributions, you have a shorthand notation. You don't always write x is distributed according to a Bernoulli with the following parameter, like this. So this tilde, it means that x is distributed according to a Bernoulli function distribution with the parameter mu, and then you take the probability mass function of this x, but you usually just write in a shorthand notation that you have a Bernoulli PMF of x with given a parameter mu. And now here's a very useful equation which takes this case distinction here and puts it into one single formula, because that's much nicer to calculate with. And if you look at it, here you can see why it's useful to use 0 and 1 as encoding. If you have a 0, then you have mu to the 0, which is 1, and 1 minus mu to the 1 minus 0. So it's 1 minus mu to the power of 1, and that's 1 minus mu, and that's exactly this case here. And if you have x equal to 1, then it's exactly the opposite. You have mu to the power 1, which is mu, and 1 minus mu to the power of 1 minus 1, that's to the power of 0, and that's just 1. And so you have encoded this case distinction in one line, and that makes calculations easier. And that's the Bernoulli distribution. Very simple. The next distribution we are going to look at is built on top of the Bernoulli distribution, and it's the so-called binomial distribution. It models the process of repeating a Bernoulli experiment n times. So consider the coin example. If you want to see if the coin is fair or not, you want to throw it 10 times, and what is important is the number of heads or the number of successes, and not the order of these successes. And that's what you can do with the binomial random variable. And so the binomial random variable, it has two parameters. The first one is the integer n, and the integer has to be at least 1. So you have to have at least one trial of this random experiment, and you have to have a second parameter mu, which is the success probability of the underlying Bernoulli experiment. And one important thing these n trials, they are assumed to be independent. That is to say, knowing that the first one was a success, I don't know anything about the outcome of the second one. It's not influenced by the first success. The PMF, you can find it on the bottom of the slide, and it's defined for all integers between 0 and n, because if you do n trials, you can have between 0 and n successes. And maybe you recognize the second part of this PMF. This one looks very similar to what we had before in the case of the Bernoulli, except that we had, instead of this n, we had a 1. So the Bernoulli is also a special case of the binomial if you pick n to be 1. And this extra factor, n choose x, comes from the fact that you're only interested in the number of successes and not in the order. And if you remember combinatorics, that's what the n choose x expresses. It expresses how many ways there are to have x successes in n trials. And on the right hand side there are two pictures. The first picture is are some PMFs for different values of the parameters. So it has this kind of bell shape. And the second picture are the corresponding CDFs. So all red points in the CDF correspond to red points in the PMF in the first picture. But there's one little difference. The PMF is only defined on the red dots, but maybe if you look closely you can see that the CDF is also defined for values in between. It's just constant with the previous integer value. That's because the CDF is always defined on the whole real line. Now we've seen the binomial distribution, and let's think of a case where we might like to use the binomial distribution. Let's look at the number of mutations in a DNA sequence. Typically such a DNA sequence has a length of 10 to the power of 9, so the big N, the capital N, will be 10 to the power of 9. And such a mutation is quite unlikely, so the mu parameter is 10 to the minus 9. Now, this would be a typical case where we would like to use the binomial distribution, but if you look at it with the numbers that I just lined out, then you will see that the binomial distribution will break down simply due to numerical reasons, because n choose x for n as big as 10 to the 9, you cannot calculate it. Because n choose x is made up of factorials, and it's impossible to calculate the factorial of 10 to the 9. It's simply too big. But luckily there's the Poisson distribution, and the Poisson distribution is an approximation of the binomial distribution for a very large n. And you can show that if you choose the parameter lambda of the Poisson distribution as n times mu, then for very large n, it's pretty much the same. And if you look at the PMF of the Poisson distribution on the right hand side, then you see that its shape is already quite similar for very small values of n. And the Poisson distribution has the following PMF, and it also still has a factorial, but this factorial is just the number of successes. And this is much simpler to calculate for large n, because the large n doesn't even occur anymore. The distributions we have looked at so far were three discrete ones: the Bernoulli, the binomial, and the Poisson distribution. From now on we're going to look at continuous distributions, a couple of them, and the first one is the uniform distribution. The uniform distribution actually also exists in the discrete case, but it's not very interesting there. And we've also implicitly used it already. It's just this idea that if you have 6 values as a die outcome, then the uniform distribution tells you that the probability is 1 over 6. And we will generalize this now to the continuous case. In the continuous case, a random variable that is uniformly distributed has 2 parameters a and b. These are real numbers, and the only restriction is that a has to be smaller, strictly smaller than b. So a and b span an interval in the real numbers, and the random variable x takes values in this interval a, b with equal probability. And so it's not a big miracle. The probability density function now, because it's a continuous random variable, is just a constant value. And this is 1 over b minus a. Why is that the case? Because the width of this interval is b minus a, and the area under the curve, which is this rectangular block, has to be 1. And so its height has to be 1 over b minus a. And on the right hand side you have depicted the PDF and the CDF of the uniform distribution. So the uniform distribution was the first continuous distribution that we looked at, and the second one will be a bit more interesting. It's the exponential distribution. And the exponential distribution, it models the time until an event occurs for the first time, and this is also again usually referred to as a success. So a typical example would be you are waiting at a bus stop, and you could model the time you need to wait as a random variable that is exponentially distributed. And another example could be the time until you expect, or the time until a machine breaks down. It's questionable whether you can talk about success in this case, but it can be modeled through an exponential distribution. And the exponential distribution has a positive real parameter lambda. And this parameter lambda corresponds to the expected number of successes in 1 unit of time. So if you expect 6 buses to come in 1 hour, and your time unit is 1, then your lambda is 6. If your time unit is 10 minutes, then your lambda will just be 1. That depends on your modeling. And of course the waiting time is positive, because the time you start waiting is usually taken as 0, and then the PDF of the exponential distributions is very simple. It's just a scaled inverted exponential function. The next thing we're going to look at are the so-called normal or Gauss or Gaussian distributions. And these are extremely popular and extremely famous. First, one thing on the naming of these distributions. Mathematicians usually call them normal distributions. In the machine learning community, usually they are called Gauss or Gaussian distributions. That's just a fact. There's no explanation to this, but just don't get confused if you start reading into literature or into papers. Normal and Gaussian distributions, they're actually the same. And a normally distributed random variable has 2 parameters, namely mu and sigma squared. And mu is just a real number, and it corresponds to the mean. And sigma is a positive parameter, and it corresponds to the standard deviation, and we know that the standard deviation is the square root of the variance, so sigma squared corresponds to the variance. So what we do with the normal distribution is we fix the mean and the variance, and that's all we need to specify this particular distribution. And they are so extremely popular because there's the central limit theorem, and this one tells you that if you have a lot of experiments and you take the limit of them, the sum of them, and you average them, then you will end up with something like a normal distribution. And normal distributions are so nicely and well behaved and have so many good properties that it's impossible to study all of them right now. But we will use the Gaussian or normal distributions throughout the course, and you will get to know all the nice properties. We will in fact have an extra lecture on the multivariate case of normal distributions. Two more distributions to talk about in the continuous case. The first one is the beta distribution. The beta distribution doesn't really have a real-world interpretation. There are some, but it's mostly used in the following case, namely, if you want to have a probability distribution of the parameter of a Bernoulli distribution. So the Bernoulli distribution has a parameter mu, the probability, the success probability, and this one itself can be modeled through a beta distribution. The mechanism of how this works will be shown in another lecture, but we will now look at the beta distribution. The beta distribution has two parameters a and b. They are real numbers and they have to be positive. And then you have the PDF depicted down here. And if you look at it, it kind of resembles the one of the binomial distribution, because the gamma function, this is a capital gamma, and the gamma function is a generalization of the factorial. You have that the gamma function evaluated at n plus 1 is in fact n factorial. If you have an integer n, but you can also evaluate the gamma function at 2.5, and you can't do that with a factorial, so it's a generalization. And so if you think of these gamma functions as factorials, then this here is roughly a plus b, choose a. And then it looks very similar to the binomial. Because of this, it's very well suited for this task of modeling the probability parameter of a Bernoulli or of a binomial distribution. And the reason, or one more reason or intuition why you would want to have such a distribution on the parameter is the following. Look at the coin toss. If you want to check whether it's unfair or not, then you wouldn't assume that all the probabilities for heads and tails are equally likely, because if the probability for heads was 1, then you would quite soon and easily see that it's unfair, because you would throw 100 times and you would have 100 times heads, and that's easy to detect. So if someone wants to build an unfair coin, they would probably choose a coin that has a success probability around 0.5, but in their favor. And that's what you can model with a beta distribution, that the probabilities around 0.5 are more likely than the probabilities around 1 or around 0. But we will come to this example in one of the upcoming lectures. One more distribution for now, namely the gamma distribution. The gamma distribution is used in a similar setting as the beta distribution, namely to model the parameter of another distribution. in this case, it's the precision, which is the inverse variance of a Gaussian distribution. Now, the gamma distribution also has two parameters, a and b, and it's defined for x's greater than 0. And again, we have this gamma function in the PDF, which is the generalization of the factorial function. And we will also see with the gamma function that it's useful to make better models than just with a univariate Gaussian distribution. And we will see this in a couple of lectures. One thing to notice about the gamma distribution, for example, if you look it up on the Wikipedia page, if you want to know more about the gamma distribution, you have to be extremely cautious because there are two gamma distributions. They are the same, but they have different parameters. Namely that the b is sometimes also used as the inverse of b. So sometimes the parameter is just the inverse of b. And you shouldn't get confused with this because this can mess up your results completely. And the usage of the gamma distribution will be clearer once we know more about Bayesian statistics. This last slide is an overview of the probability distributions we have seen so far, and it wraps up this short chapter on univariate distributions. It gives you all the information we had on the previous slides in a table if you need to look it up, like the parameters and also the codomain. The codomain is the values of the random variable for which the PMF or the PDF is defined, and you also have the PMF or the PDF. And you also have, as an addition, the mean and the variance of the respective distributions. And if you want to practice, you can try to calculate these means and variances from the respective PMFs or PDFs. But this slide is also a good point to summarize what we've done so far. What we've done so far is the following. We've formalized our concept of uncertainty by defining probability spaces. And then we've examined these probability spaces and found properties like, or things like the conditional probability or the multiplication law and so on and so forth. And then to make our lives easier, we have introduced random variables because these random variables work as proxies to probability spaces. And once we had these random variables, we could have a look at these distributions that you can see in this table on this slide. Now, what is still missing? Well, we haven't talked about using multiple random variables at all. We cannot use still some of the stuff like conditional probabilities and independence and so on. Because we just haven't talked about what it means to have multiple random variables. And this is going to be the last part of this introduction to probability theory for machine learning, how to work with multivariate random variables.